So to repeat, now that it's being recorded, I'm grading exams. Hopefully they'll be graded by the end of the day. And we're moving into Unit 2 because Unit 2 will cover the content for Exam 2. I did get a few emails last night and early this morning that some things were not quite right with like the Respondus browser, so I've reached out to Distance Ed, and she's already emailed me back about that. She's kind of telling me what may have gone wrong and what we need to change for next time. So this is all kind of a newer thing for me. We used this in the end of the spring semester, but yeah, and I promised I did training on it, but it's we're still having issues. So anyway, if you do find yourself having any trouble, let me know. Are there any questions about the exam before we start new content? I'll make the feedback from the exam grading available after I'm done with everybody's. And we're in Exam 2 content now, so we're in Unit 2 material. The labs are already posted and available. That includes the alternate labs. So if you did not buy the lab kit for whatever reason, that's fine. You have alternates. I think it's labs 4, 5, and 6 in this unit. So I tried to make them as comparable to the lab kit as I could. All right, but if anything does come up, if you do have questions at all, please let me know. This section sometimes is easier for people. Sometimes they really like this unit because this will contain blood, the heart chapter, and then blood vessels too. So I see Jasmine's coming in too. We're going to get started and we'll go through, but if I'm going too fast, you can always watch this again later, or just feel free to type out a question or just kind of interrupt me, and that's fine. Okay. So for blood, this is the vehicle for the cardiovascular system. It's hard at this point because you haven't quite had blood vessels yet. That's coming in a later chapter. But blood vessels, just generally speaking, include arteries, capillaries, and veins. And so an artery, we've said this with the fetal pathway, an artery always travels away from the heart, and veins always travel toward the heart, and that does not ever change, right? Now, what does change is whether or not they contain oxygenated blood or deoxygenated blood. Capillaries are kind of between the two, generally speaking. Capillaries are the site of exchange. Exchange happens in capillaries, and that's by diffusion. So if you remember back to AMP1, diffusion is the movement of a substance from a higher to a lower concentration. That's what's happening there, and more of that will come when we get maybe toward the end of this unit in blood vessels, but also in the respiratory system chapter. So this will tie in with everything you'll do. You could really do the blood chapter along with any other kind of chapter. All right, but we'll get more into this anatomy later. Okay, so that's kind of the roadway, you know, the arteries and veins and capillaries. The vehicle, the car that's driving along within this system would be blood. And so there's different types of cells in blood and other components to make it carry out its functions. This is a very important slide. Blood's pH will come up over and over and over again, I promise you, until the last day of the class. It'll be on your final exam. So you need to go ahead and know that the blood pH is roughly between 7.35 to 7.45. That range is a normal value. That's slightly alkaline, but that if blood was to deviate one way or the other above or below that, then the body would change pH in a drastic way, and that could cause some negative outcomes. But we'll get into that later with buffer systems. Blood is about 8% of our body weight. You don't have to know that figure. Blood is very viscous, which means that it's thick and it's more resistant to flow. So viscosity, more will come with that too, but that's kind of a resistance to flow. It's a thickness of blood. And later, I think in the blood vessels PowerPoint, I have this image of a just kind of sink with water running from the tap versus a tube of honey, and the person's kind of letting the honey run out of the tube. And so honey is much more viscous, is the visual you get from that. Blood makes up about 5 liters of fluid in our body. It varies between male and female, though, and so there are some other factors there at play, and it's a fluid connective tissue. My goal for the day 2 is just to kind of get through this PowerPoint, and then tomorrow in that lab, we'll go through more of the anatomy stuff, the lab content. What are some of the functions of blood? Distribution of solutes is a big one. So blood's going to function to carry oxygen, also waste, and as you know now from the last unit, hormones. Blood also allows for exchange of these materials like oxygen and carbon dioxide. The substances that are dissolved in blood are called solutes, and the solvent does the dissolving. And so we'll see later that a lot of blood is plasma, and plasma, a lot of that is water. And so water is a universal solvent. It dissolves solutes, and it does it really well. So it's going to be able to carry these solutes throughout the body. Blood also functions in regulation of pH, temperature of the body, and fluid homeostasis. And blood helps out with protection from infection, and that's largely with the help of white blood cells, which we will talk about. It also prevents against fluid loss. It provides us help with blood clotting after damage to a blood vessel wall, as well as regulation of blood pressure. And we could go on and on here and talk about more functions, but these are just a few. All right. What is blood made of? I thought I had another image from your text, but I don't. But there's a similar picture of this in your textbook. The components of blood are nicely kind of seen when you break out this vial of blood and just kind of look at the different parts that kind of settle out. So the matrix of blood is a fluid plasma. Plasma makes up roughly 55% of blood, so over half is plasma. And we'll talk about what's in plasma in the next slide or two. We'll go through fibrin also with that. So what else is in this sample? There is an area called the buffy coat there in the middle. That's about 1% or so. That contains white blood cells or leukocytes and platelets, which help out with sealing a break in a damaged blood vessel wall. And then lastly, down at the bottom are the erythrocytes, the red blood cells. They make up about 45% of a blood sample. This varies, again, based on is the person male or female. So this percentage of a sample that is only red blood cells is called hematocrit, and some of you may have heard that before. That's a good lab value to have, just to indicate, you know, does a person have anemia? Is something going on with their fluid loss? What's going on with a person clinically? So hematocrit is a very important thing to know. Again, it's the percentage of a blood sample that contains only red blood cells. In males, it's a little higher. What hormone do you all think causes males to make more red blood cells? I'll give you a second. Testosterone, right? Testosterone. Testosterone influences the release of erythropoietin. And so erythropoietin is back in this unit. We'll go through and talk about the feedback mechanism with erythropoietin in just a bit. All right, so we've talked about what is blood made of, but now we're going to focus on one part of it, 55% of it, which is plasma. So plasma is about 90% water. All right, and we've talked about this loosely already because we have talked about things like ADH and aldosterone, which are going to facilitate the reabsorption of water. That was a test question for some of you. when water is reabsorbed into the body, it's added to plasma, and so that increases our blood volume, but also then subsequently increases blood pressure. Well, I'm getting ahead. Let's get back to plasma for a minute. Plasma is about 90% water. About 1% or so is dissolved solutes, and there's not just like one dissolved solute like sodium or potassium. There's over 100 different types of kind of particles in there. And about 9% remaining represents the plasma proteins made by the liver. There's different classes of these. Usually they'll end with that suffix globulin. And so you'll see that kind of commonly come up. So the immune proteins are immunoglobulins, also known as antibodies. And that's a big part of this unit. There's also clotting proteins in plasma, which include mainly fibrin. You'll see later that fibrin is going to form a mesh over a blood clot. And the main plasma protein, the one that's most prominent, I should say, is albumin. Albumin's job is to create an osmotic gradient, and so it's going to pull water into the plasma. It helps to maintain that water homeostasis within plasma, and that is called osmotic pressure. When it's able to pull water in to plasma, that's osmotic pressure. All right, and feel free again to interrupt me anytime or ask questions, but I will post this in an hour or so after class when it's available. Okay, red blood cells, erythrocytes. These are unique in their shape, and you can kind of see them here. They have this biconcave disc shape, so they look kind of like an inner tube or a donut, but the middle part is not completely removed. This helps to have increased surface area for the red blood cell. The plasma membrane of the red blood cell is held in place with the help of something called spectrin. Erythrocytes are made in response to the hormone erythropoietin from the kidneys, and they are just essentially bags of hemoglobin. That's all they are. Erythrocytes are pretty unique because as they become a mature cell, they eject their nucleus and they really don't have any organelles. So what they are left with is plenty of room for hemoglobin. So there's millions of hemoglobin molecules in one red blood cell. And what does hemoglobin kind of look like? Let's go through that next. Hemoglobin has 4 polypeptide chains. You can see them here. 2 are alpha, 2 are beta. They're darker in color up at the top, so you can kind of delineate which are which. Each polypeptide chain contains 1 heme group. Each heme group contains 1 iron, and that's represented with its atomic symbol Fe. Each iron can bind to 1 oxygen. Therefore, 1 hemoglobin molecule can carry 4 units of oxygen. All right, so hopefully y'all can hear me and you'll answer this. Let's say that a red blood cell has 1 million hemoglobin molecules. How many molecules of oxygen can it carry? Good, yes, good, thank you. All right, awesome. Now, when hemoglobin has bound to oxygen, and more of this will come when we get to the respiratory system, but when it carries oxygen, it's called oxyhemoglobin. And that's the main way that oxygen is transported. About 98.5% of it is carried in that way. Carbon dioxide is also carried attached to hemoglobin. Not as much, but it can be transported in that way too, bound to hemoglobin. And so, like I said, it's good to have that baseline and understand that now, but more will come with that physiology in the respiratory system chapter. All right, more about hemoglobin. When it releases oxygen, it's called deoxyhemoglobin. Carbaminohemoglobin is the term for hemoglobin that is bound to carbon dioxide. And again, not much of CO2, about 23% or so is carried in that way. Carboxyhemoglobin is what hemoglobin is called when it is bound to carbon monoxide, and it really, really loves carbon monoxide. Hemoglobin has a really high affinity for carbon monoxide. And affinity is a new word. It's kind of a funny word. It means like an attraction for or a willingness to bind to it. And so hemoglobin, given the choice between oxygen and carbon monoxide, has a higher affinity for carbon monoxide, so it's going to choose to bind to that, which is why carbon monoxide, one reason why it's so dangerous. It's taken the place where oxygen normally could bind, right? So, all right, so let's go through erythropoiesis. This is the formation specifically of red blood cells. The lineage and the creation of blood cells is pretty complicated in my opinion. I don't normally test really heavily on this section, but I would just kind of know the main parts that we go through together. So if you haven't done it already, I think that printing the PowerPoints, if you're able to, or at least taking your own notes as we go through on paper and then reviewing them later, will be a good thing. So hematopoiesis is a larger kind of process in which blood cells, generally speaking, are formed. Erythropoiesis is specific for red blood cells. And this happens, of course, in red bone marrow. So you kind of learned that back in A&P 1. It all starts with stem cells, and generally they're called hematopoietic stem cells because they can become anything. They have to have some factors that are kind of thrown in there to stimulate them to become specific types of blood cells. Erythropoietin is going to stimulate, again, the production of red blood cells. All right, how does this happen? What's kind of the loop here for the formation of red blood cells? Well, you know, generally speaking, the stimulus for this whole thing is a drop in blood oxygen levels. A drop in blood oxygen levels. And that is called hypoxia. Hypoxia is a drop in blood oxygen levels. So why does this happen? Well, let's say the person has lost a lot of blood. They don't have as much red blood cells then, therefore they don't have as much hemoglobin, so their blood is not able to transport as much oxygen to their brain or any other tissue. All right, let's also say that maybe they have less hemoglobin or they have less iron in their blood. Maybe they're anemic for some reason. And there's different types of anemia, okay? But anyway, that's the stimulus. They have a drop in oxygen carrying capacity of blood. And so that's the initial stimulus. That's the imbalance here in the seesaw. And that causes the kidney to make EPO. EPO stimulates the production of red blood cells in the red bone marrow. And so the number of red blood cells will go up. And therefore, the oxygen carrying capacity of blood goes up, and so hopefully blood oxygen levels go back to a normal range. All right, so that's the whole kind of feedback loop of this. What I did not say is that, of course, when blood oxygen levels get back to normal, do we need more EPO to be released? No, we're back to normal. We don't need too many red blood cells. That would be a bad situation because too many red blood cells would make blood more viscous and would lead to clotting and that sort of thing. So that would not be good. All right, red blood cell formation is seen here in this loop, just generally speaking. Again, the stimulus is hypoxia, but that could be caused by any of these things. It could be a drop in oxygen levels. Maybe a person is at a high altitude where they're not able to get as much oxygen from the atmosphere, or maybe they are just in another situation where it's not available. Maybe they have less red blood cells, iron deficiency, where this kind of goes hand in hand with this one. There's limited oxygen available. All right, that's going to stimulate EPO release in this whole loop. So what does that look like in the red bone marrow? Again, it all starts with the stem cell, and stem cells will become an erythrocyte CFU. That means that they're destined to become, they're committed now to becoming a red blood cell. Then they will become a pro-erythroblast, which will then become an erythroblast. And what you see here is that as that red blood cell is working its way toward maturity, it is going to release its nucleus and organelles, and then it becomes a reticulocyte. Reticulocytes are going to join into the bloodstream, and finally they become a mature erythrocyte. How much of this whole step-by-step process am I going to put on your exam? Maybe one question, and it won't be like a short answer question. Hopefully that makes people feel better. What I do expect you to know from this for sure is this loop. And I think it makes sense. We have a drop in oxygen level, so the kidney makes EPO, so red blood cells make more red bone marrow makes more red blood cells, and oxygen carrying capacity goes back to normal, and there we are. All right, but make sure to read through this section for sure. Now, red blood cells live for about 120 days, and so they are destroyed, and that mainly happens in the spleen. The spleen is really good at this, and later when we do the blood vessels chapter, we'll talk about the types of capillaries. Sinusoids are a very leaky capillary, and they're able to trap things that are moving through really easily. So normally these old or damaged red blood cells become trapped in the spleen, in the sinusoids, and then macrophages, which literally means big eater, these cells will come in and destroy the red blood cells. They'll break them down. Now after that, then the components of the red blood cell mainly are going to be recycled and kind of reused, or some of the parts will be excreted, but bilirubin is going to become available because of a breakdown of hemoglobin. Bilirubin has a complicated kind of excretion pathway. Part of it will become bile, which is going to come back in the digestive system unit. Iron is removed from heme, and a lot of iron is reused to make more hemoglobin. And then the amino acids from those polypeptide chains are used to build new proteins. So a lot of the breakdown products are then reused. All right, some disorders, and some of these are not really mentioned. Well, I think all of these are in your textbook. First off, anemia just generally means a drop in oxygen carrying capacity. Some signs or symptoms include pallor, which is a whiteness of the skin, feeling fatigued or weak, and then shortness of breath, which is a pretty funny medical abbreviation. No offense to anybody. Okay. Hemolytic anemia, I will come back to that when we do the blood typing later at the end, and if I forget somehow, somebody please remind me. Sickle cell disease is pictured here, and in sickle cell anemia, there's a genetic cause of this that's going to cause the shape of red blood cells to be different. They're not that biconcave disc kind of shape, but they're sickled in appearance, and so that causes them to become clotted more easily, and that causes disruption in flow, which can lead to other complications like strokes. Other disorders again include low levels of hemoglobin, which can lead to anemia, and low hematocrit. And there are different causes of anemia. We'll talk about another type when we get to the digestive system, for example. All right, before we keep going, are there any questions? I'll kind of give you like 30 seconds to pause, ask questions, and then we'll keep going. Okay, moving on then to white blood cells. Leukocytes. These are complete cells, meaning they do have organelles in a nucleus. They largely function in immunity. And a few terms to kind of keep in mind here that will come back in chapter 20 when we focus on the immune system include diapedesis. Diapedesis means that cells can kind of squeeze through a capillary wall. And so they can squeeze through the capillary wall to move to a site of inflammation, for example. Other terms here include chemotaxis. You may have heard this when we did the fertilization section, because this is when cells move to an area that contains chemicals that attract them to the area. So when there's inflammation in the body, inflammatory mediators are released and they will attract white blood cells to come into the area. Also, leukocytosis means the production of more white blood cells. Okay, there's two big classes of white blood cells. They are either granulocytes or agranulocytes. Granulocytes contain granules in their cytoplasm, and agranulocytes don't, and that's it. So we'll go through all of those, and then I'll tell you what this acronym means. Okay, so the granulocytes, my kind of trick to remembering them, you can either remember the name Ben, like Ben eats grains is how I have to think about it. They include basophils, eosinophils, and neutrophils, or that they end with the suffix phil. Phil eats grains, whatever works for you. These are spherical, they're bigger than agranulocytes, generally speaking. They have a lobed nucleus, so their nucleus sometimes looks like there's more than one, but there's not. It's just multi-lobed. They do, of course, contain granules that stain a darker color, so they're easier to kind of see. For the most part, they're phagocytic. Your book says that here, but then in chapter 20, they kind of say something different. So that's, to some extent, they're phagocytic. We'll say that. All right, so what do they do? Neutrophils are bacterial slayers. They are the most common white blood cell. They are also called PMNs, or polymorphonuclear leukocytes. If you break that down, it means many-shaped nucleus, and that's a telltale sign that this is a neutrophil. The nucleus looks crazy. It looks like there's 5 of them. They are one of the first kind of responders that goes to a site of inflammation. So big thing to know right now, they're most common, they're granulocytes, and they slay bacteria. Eosinophils are not as common, and they're the second least common, if that makes sense. We'll go through that later. They have a bilobed, 2-lobed nucleus, and they're really, really good at attacking parasitic worms. All right, so I always include this. If you know the movie, type it out. All right, lastly for granulocytes, basophils are the rarest white blood cell overall. They release histamine, which is a vasodilator, and they have a U or S-shaped nucleus, and it's hard to see it sometimes because of the granules. They also produce heparin. Agranulocytes don't have granules. They have more of a sphere-shaped nucleus, and include the sites. Lymphocytes, which are the second most common white blood cell. These include T lymphocytes and B lymphocytes, or also known as T cells and B cells. T cells attack viruses and tumors. B cells produce antibodies, and we'll go through more detail with that in chapter 20 later. Monocytes are the biggest white blood cell. Some of them are destined to become macrophages. So as they become older and more mature, they'll develop into macrophages. These clear up lots of things: chronic infections, bacterial parasites, viruses. So yeah, more to come in chapter 20, a lot more. Let's go back to this acronym. If you break it down, and if you want an acronym to kind of remember what's the most common to the least common white blood cell, you could remember never let monkeys eat bananas. So neutrophils, lymphocytes, monocytes, eosinophils, basophils. That's the list from most common white blood cell to the rarest. All right, and in lab tomorrow, we'll go through what these look like some more. Disorders include leukopenia. That's a low level of white blood cells. A lot of times that happens because of anti-cancer drugs. Leukemia is a proliferation of a certain type of white blood cell. Those are named based on, is it chronic or acute, and then what type of stem cell is affected. And mononucleosis is a viral thing where the person becomes very, very fatigued. It's a long-lasting condition. Epstein-Barr is what it's commonly known as, and some of you may have had this before, but we'll try to look at some white blood cells stains of this tomorrow. Next, last, I think, but not least, platelets. Platelets are not a cell. They're just fragments of a big cell called a megakaryocyte. They play a role in clotting, and they are released because of a substance called thrombopoietin. All right, which brings us to hemostasis. And so later what I'm going to do when I post this video is I also will post some other videos from YouTube that show this process kind of step by step. Hemostasis literally means stop bleeding or blood stoppage. And so this is what causes us to stop bleeding after we have cut ourselves or had some sort of injury to a blood vessel wall. This is a fast, localized thing, and it's mainly controlled by clotting factors. These are the 5 steps laid out. We're going to go through them, and it does kind of take some practice. So we'll go through it together a couple of times. And this is probably the first big physiology for this unit you've had. All right, so imagine that you're doing something, maybe you're getting ready for dinner and you accidentally have a cut on your hand. The first step that would happen in stopping bleeding would be vascular spasm. Step 1, vascular spasm. You haven't learned this with me yet, but in the wall of blood vessels there's smooth muscle, and so that smooth muscle will contract during this spasm, and that causes the blood vessel to narrow. It becomes constricted. The purpose of that is to stop the blood flow to that area, not completely, right, but to narrow it down, and so that way we're not losing so much blood. Okay, so that's step 1. Step 2, platelets form a plug. That is called aggregation. Aggregation. Platelets are going to become more sticky thanks to this factor called von Willebrand factor. VWF is way easier. That causes them to become more sticky, and they're going to adhere to each other, and that forms a plug of platelets. And they seal the broken space in the wall. They form a plug. All right. Next, step 3. Step 3 is probably the most complicated. Coagulation. I'll give you the gist of it, then we'll go through the step by step. What you need to know is, at the least, is that coagulation causes the formation of fibrin in a mesh network of fibrin threads. And that's going to trap red blood cells and trap platelets and kind of solidify a clot. All right, so you can kind of see that here. This picture, I think, is from your textbook. It's a really, really good one, and your book breaks it down really, really nicely. All right, so one more time, we'll kind of go through what happened initially. So we have some sort of injury. Blood is leaving. You can see blood cells leaving here. So first step, vasoconstriction or vascular spasm. The wall becomes more narrow. Next, platelets become activated. They become very sticky thanks to von Willebrand factor and form a platelet plug, an aggregation of platelets to seal the broken wall. Next is the coagulation cascade, which is kind of complicated, but ends up with the formation of fibrin threads that surround the plug to form a blood clot. They're going to help to add some red blood cells and more platelets to that clot. All right, so let's talk about coagulation next. All right, and I'm trying to get to my favorite section, my favorite slide, but apparently I don't really have one. All right, so let's talk about coagulation and how this all starts. And if you read your book, you may get lost, so just stick with what we go through together. There's 2 pathways to start off coagulation. There's the intrinsic and extrinsic pathway. What does that mean? One of these pathways contains everything that is needed to make clotting factors already there locally in the blood. That's the intrinsic pathway. The extrinsic pathway has to pull some substances from other places in order to create clotting factors. That's the extrinsic pathway. They both end up with the same product. So both pathways will get to the same end result, and that's a factor, a clotting factor called factor X or factor 10. So factor 10 is going to quickly become factor 10A, which combines with calcium, and it is going to form something called prothrombin activator. Prothrombin activator. All right, let me just look through for 1 second. I thought I had something better here. Maybe not. Okay. All right, factor 5A will help out with that a little bit too, to form prothrombin activator. But that's the first kind of step in this whole process. Prothrombin activator, you could probably guess, will activate prothrombin, which becomes thrombin. And when thrombin is formed, it turns fibrinogen, which is inactive, into the active fibrin. All right, so I'll say that again. The two pathways come together to create factor X, factor 10, whatever. That now joins into the common pathway, meaning it was the same end product, and the goal now is just to make fibrin. That's the end goal. So factor 10 is going to combine with some other factors to become prothrombin activator. Prothrombin activator turns prothrombin into thrombin. Thrombin then activates fibrin from fibrinogen. Once you have fibrin, these are these protein threads that are going to go and surround the platelet plug. They help to trap red blood cells in the plug. They help to trap more platelets in the plug. They kind of solidify a clot. And now we have our good clot. That's coagulation. All right, and if you're like, read it, watch this again, watch the videos I'll post, and it will help you. What you don't need to know here are all the clotting factors, because these are complicated. They're not named in order. They're numbered in the order that they were discovered. And so it's not like cranial nerves where they have an order and rhyme and reason. They're different. So you don't have to learn every single clotting factor. All right, what happens next then? We've got this clot. It cannot hang around forever. And so step 4, what happens is clot retraction. The clot becomes smaller. Think about a dish rag in your sink, and if you were to squeeze that rag, there's some water that seeps out, and the rag looks like it becomes smaller. It becomes smaller in size, less surface area, whatever. That's what happens with this clot. When it retracts, this fluid is released from it called serum. Serum is basically plasma minus the clotting proteins. That's essentially what serum is, and it seeps out from the clot. The clot becomes smaller too at that time, and so that's going to allow the damaged blood vessel walls to become closer in proximity to each other. That's going to promote healing. When those damaged walls come close together, of course, that's going to make it easier for the wall to be rebuilt. There's also some growth factors that are released at that time that stimulate this rebuilding of the wall. Lastly, step 5, after a period of time, thrombolysis happens. Thrombolysis is also called fibrinolysis. If you watch the old recorded lecture I've got posted, and I think I have a slide for that that kind of shows you what happens at that time. So this is caused by plasmin. Plasmin is released because of the help of something called TPA, tissue plasminogen activator. And I'll type it, but I'll also kind of write it out later if I need to. Tissue plasminogen activator. That just does what it says. It activates plasminogen into plasmin. And plasmin's job is to go and degrade fibrin, break down fibrin threads. And so that dissolves the clot. that dissolves the clot. All right, so I'll give you a minute to think about hemostasis and any questions you have about that. Yeah, so I'll give you like 30 seconds. Okay, this slide also just shows you how plasmin is made. It uses the term fibrinolysis, which seems to be synonymous from my reading with thrombolysis. Plasminogen, of course, becomes plasmin with the help of tissue plasminogen activator. Plasmin goes and breaks down fibrin into just fragments of what it was. And that's the dissolution of the clot. Okay. Some disorders, a thrombus is a clot that forms just kind of on its own, and that stays in one spot. If it becomes dislodged and it travels throughout the body, that's an embolus. And of course, sometimes those travel to the lungs, to the little pulmonary capillaries, which is called a pulmonary embolism, and is a very, very dangerous situation. Thrombocytopenia is a low level of platelets, and that can happen for various reasons, and obviously is going to interfere with blood clotting. And hemophilia is a genetic condition in which there's a lack of clotting factors, one or more, and so that's going to slow the process of hemostasis down. And if you really want to see a genetic trace of this, there are some pedigrees you can look at that are done with the royal family to kind of trace this condition. And I'll post that if anybody wants it. Okay, last big physiology section, then I promise I'll leave you alone for a while. I'm also going to post some links about this, including a game that you can play. I think it requires like Flash maybe, or Adobe, I don't know, but I'll post it for you guys later. Blood typing. Okay, we're going to go through the ABO system of blood typing, and then we're also going to talk about the RH factor. There are other blood typing systems, but this is the most commonly used system. So we have to talk about some A words first, and that includes antigens and antibodies. Both of these things are just like proteins, essentially. Antigens are protein markers on the surface of a red blood cell. Whatever antigens you have determines what your blood type is. The types of antigens that there are in the ABO system with the RH are A antigens, B antigens, and RH antigens. The RH determines if your blood is positive or negative. If you don't have the RH antigen on your red blood cells, you have negative blood. Personally, I have A positive blood, so what type of antigens do I have on my red blood cell surface? I have A and RH. I have the RH factor, so I have positive blood. Okay, now antibodies are hanging out in the plasma. Remember, those are immunoglobulins that are floating around in plasma. We talked about the types of proteins in plasma earlier. These will respond in a negative way, of course, to something foreign that comes in. So if you have foreign antigens that are donated to you in a transfusion, then antibodies would attack them. So there's specific donor-recipient combinations, and we'll go through scenarios with that quite a bit. We probably will do more tomorrow, just time-wise, so I'm not loading you down today too much. But if antibodies respond to foreign antigens, they will clump together in what's called agglutination. Agglutination is the clumping of antibodies to antigens in a donor-recipient match that's not a compatible match. Basically, the gist is here, you will have antibodies against anything that is foreign. So in my blood, for example, I have A and Rh antigens. I would have antibodies against B. All right, so we'll go through a lot with this. We'll do a lot of practice because this, I think, is a tough physiology. This may be a little bit more confusing to some people than hemostasis is. We've already said that Rh factor is a protein, and if a person have Rh, they're negative. I'm sorry, they're positive. If they don't have Rh, then they're negative. They have a negative blood type. If you have Rh negative blood, then you would make antibodies against the Rh factor. All right, so think about that. If you have Rh negative blood, you will make antibodies against Rh because you would recognize that as a foreign antigen. So a person with negative blood type won't be able to receive positive blood because the person with the negative blood would have antibodies against the Rh. And agglutination would happen between those anti-Rh antibodies and the Rh antigen that came in the donor blood. All right, so, and there's hemolysis again. We'll come back to that. All right, I won't forget, I hope. So, two things from this slide. AB positive blood is a universal recipient. They have blood cell surface. So they can receive anything. They don't have antibodies against anything because they have all these antigens. So they're not going to recognize A as being foreign or B as being foreign. So they can receive any type of blood. O negative is the universal donor. They have no antigens on the red blood cell surface, so they can give blood to anybody. All right, so we'll go through some scenarios, and I do have some pictures in here to help kind of break it down. Personally, these don't help me. I have to kind of think through it. I just can't remember these. But let me show you a blank whiteboard. All right, let's go through and pretend that we have a red blood cell. Pretend that looks like a red blood cell. And that on the surface we have Rh and B antigens. All right, so again, what kind of antigens does this person have? Antigens. Okay, so let's go through this together. They have B antigens and they have Rh antigens. And so what's their blood type? Does anybody know their blood type? B positive. Good, good, Jessica, thank you. B positive. They're going to have antibodies against everything else. They're going to make antibodies against A because they don't have A. So if A came in, it would be recognized as foreign. All right, so can we give this person A positive blood? Can we give them A positive blood? No. Why not? No, because they have antibodies against the A, right? And so if A comes in, they're going to say, that's foreign, I don't recognize that, let's agglutinate, right? All right, so let's go through another one. And then I promise I'll post that game. I'll post a lot of links for you guys to practice this stuff. All right, red blood cell again, and let's say that they have just A's. That's it. So what type of blood does this person have? Yeah, good. A negative. Good. So they're going to have antibodies against what? Yeah, antibodies against B and against RH. Okay, so can we give this person blood that is O negative? Can we give them O negative blood? Yeah, you can give anybody O negative blood. It's a universal donor. The way I remember that too, if you need help with that, is the O's. I don't know. Maybe I'm weird. Okay. But they're the universal donor. O negative, you can give to anybody. Can we give them A positive blood? No, why not? Good, yes, because of the RH coming in, and they have antibodies against the RH, and so agglutination would happen. Good. We'll do more of these tomorrow too, during the lab kind of time. But I am going to leave you alone with that right now. I'll also post that Nobel Prize game for blood typing. And I promise it's a fun game. You have mock patients and you type their blood, and then you go through some scenarios. The other part of that, I will say, in your lab kit, it asks you to do blood typing. We'll go through that tomorrow. So I would say wait if you can, time-wise, to do that lab until after we've talked about it tomorrow, because I think hopefully it would then make more sense. So let's talk about hemolysis, though, and then we'll take any questions and we'll call it a day. Hemolysis is the destruction of red blood cells, and that can happen for various reasons. One dangerous condition, though, is hemolytic disease or hemolytic anemia of the newborn. All right, so what happens with this is that a mother, a pregnant female, has RH negative blood. She has RH negative blood. Here's what's tricky about this. So right here on the slide, I say RH negative will create antibodies against the RH factor. You have to be exposed to it, though, really, for that to happen. That's the trick to it. All right, that makes it a little bit more complicated, maybe. Okay, so this mother, she's got RH negative blood, and she has never before, had some sort of transfusion where she was exposed to RH positive blood. Therefore, she doesn't have any antibodies against RH in her first pregnancy. So let's say that she's pregnant and her fetus is RH positive blood type. They got this positive antigen from dad or whatever. Okay, we're not even going into genetics, but let's just say that the fetus has RH positive blood. Now, you know this, that their blood is not going to mix because of the placental barrier during pregnancy. However, during delivery, their blood will mix. And so during delivery, mom is now exposed to the RH factor in the fetus's blood. So now mom creates antibodies against RH. Okay, now first pregnancy was fine, everybody was good, but now second pregnancy happens. Now, let's say again, mom is still Rh negative, but the developing fetus is Rh positive blood type again. Now mom does have these antibodies against Rh, and they can cross the placental barrier. And so they can go and attack baby's red blood cells and cause destruction of the red blood cells, which can cause death. And there are drugs that can be administered to suppress this. So that's why if you've been pregnant, they'll always kind of ask you about this, and they'll type blood and everything else. But that is hemolytic disease of the newborn. All right, that's, I think, all the content I want to go through today. What questions do y'all have? Yeah, Jessica, go ahead. You might be typing. Okay. Yes. Yeah, you can. Blood type is it's a codominant trait. So yes, you can trace it back through like Punnett squares, for example. And I can send you something to kind of help you with that to show you how that's done. It may even, I think it's even in the Ammerman textbook toward the back of the chapter, I want to say. Or it might have even been in the development chapter, but it should be somewhere in your book too. I won't test you guys on that, but it is pretty interesting. Anything else?